This program is brought to you by Stanford University.
I'd like to introduce Dr. Marcy. He is a professor at UC Berkeley. He was a double major in physics and astronomy at UCLA. Graduated with a lot of Greek behind his name, summa cum laude, Phi Beta Kappa, blah, 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 blah. PhD from UC Santa Cruz, so moving north. Spent a little time in the East Coast at the Carnegie Institute of Washington. And then came back to be a faculty at San Francisco State University, and several years ago moved across the bay to UC Berkeley. He has more awards than I can possibly mention. I know Jason sent out the web link. The ones of particular interest are the Carl Sagan Award, the NASA Medal for Exceptional Scientific Achievement, and particularly impressive is he's a member of the National Academy of Sciences, which is an enormous honor. It's the highest honor for a scientist in this country that's given nationally. Of course, the thing that stood out to me was the G. Darwin Lecture at the Royal Astronomical Society. Who is G. Darwin? Oh, for goodness sakes, you know that I'm a Darwin fanatic. I wouldn't be baking all that cake on his birthday otherwise. Gary. We'll ignore that, move on. George Darwin was one of Charles Darwin's sons. Charles Darwin actually never had a PhD himself. He was never a member of the Royal Society, because that was stopped. But he had several sons who went on and did very prestigious things, including his son George Francis, who we'll hear about again, and so on. So that makes Professor Marcy practically a biologist, having given the G. Darwin lecture. Anyway, enough of that. Let me pass you over to Jeff Marcy. Let's give him a big welcome to Stanford.
Well, it's a real pleasure to be here. I feel lucky to be able to chat with all of you, and I have an audacious agenda, which is to try to cover everything I know about the formation of planets, planets that we've discovered around other stars, how those planetary systems compare to our own solar system, and I will try to spend the second half of the lecture talking a little bit about what those planets tell us about habitability on them and the prospects of not just microbial life, which will be the subject of a lot of your lectures this semester, but also intelligent life. So I have this ridiculously large ambition to cover the topics that normally would take a whole semester. Let me start with something a little controversial, if I may. I don't know what all the lectures are going to be like for the rest of your quarter, but I would like to issue a challenge to all of you. What I would suggest to you is that most scientists, whether they're biologists, chemists, or astrophysicists like myself, come to their work with some bias. They have some preconceived notions of what the answer is in their work, and that psychological inclination can influence, maybe even unduly shape the interpretation of their results, even shape the nature of their experiments and their observations, and then in turn change the course of science inappropriately for a while until the community realizes that there's some bias or mistake and corrects itself. And you're all in that position right now. You're going to hear during the quarter talks on the prospects of elementary microbial life, the prospects for intelligent life, habitable worlds. And I think you might ask yourself, as the quarter goes along, what's wrong with each of the speakers' picture? Don't just buy into what any one of them says. There's something they're bringing to the table that's a bit of a sense of the answer beforehand. Indeed, even the notion that there's an astrobiology course suggests that there's some connection between biology and astronomy, and frankly, that hasn't been proven. We don't know of any life elsewhere in the universe besides right here on the Earth. So there's already some sort of a sense that the picture might be colored. And so your job is to always question what the speakers say, and I hope you'll do so with me. Watch out for my biases. And think out of the box. Try to ask questions that are a little bigger, broader than just the confines of what the speakers are telling you. And I think my view is that the best scientists are those who are slightly skeptical, maybe even annoyingly so. And so you should be annoyingly skeptical during my talk, because I will try to bring some notions to you that you may not agree with at the outset. So let me start with the ground truth. I'm an astronomer. I hunt for planets around other stars. I've found a lot of planets around other stars, or at least I'll try to twist your arm to convince you that my team has found planets around other stars. And the question that we're trying to ask is an old one that the ancient Greek philosophers asked, and even before them, which is whether there are other planetary systems like our own solar system with the 8 major planets orbiting in circular orbits. The big gas giants are out far. Why is that? The rocky planets that are small are in close. They all go around the sun in the same direction and lie in a plane, a flattened plane that we call the ecliptic. Why is our solar system structured this way? Why is the architecture of our solar system this way? And if we can understand how it formed and how it got to be this way, then we might ask, are other planetary systems similarly structured, and are they so configured for the same reason that our own solar system is? So right away you can see some biases built in. We have our home system. Are others like that? And many people have asked this question. My favorite Greek philosopher is Democritus. He was the one who first postulated that there were atoms of which all material things are made. But he also thought about the universe, and here's a great quote from Democritus, again 400 BC. There are innumerable worlds of different sizes. These worlds are at irregular distances, more in one direction, less in another. Some are flourishing. I guess what he meant was life. Others declining, as if the civilization that he was in might be on that side of the fence. Here they come into being, there they die. He's thinking of the dynamics of not just the planets, but of the life on those planets. So he was very far-reaching. You have to remember that in 400 BC, people didn't even know that the stars you see in the night sky are suns, like our own sun, our sun being a typical star. So for them to be imagining what those stars are like and any planets around them was quite a leap. A bit of a heretic was Epicurus, who's not very well known, lived just a little bit later. They banned him from Athens, and he had to open his own philosophy school outside of Athens. And he wrote even a more fantastic thing in his writings. There are infinite worlds, not just lots of worlds, infinite worlds, both like and unlike this world of ours. We must believe that in all worlds there are living creatures and plants and other things we see in this world. Really an extraordinary quote for an era, remember, when it wasn't even clear that our Earth was round. And here these folks are thinking way outside the box. And then much later, in the 1500s, a fellow named Giordano Bruno, who I'm sure will come up several times during this quarter, he wrote a book called De l'Infinitio, etc., about the infinite size and contents of our universe. And he wrote specifically that there were other planets, life on those planets, and probably intelligent life on planets around other stars. And at that time, the Catholic Church was quite strong, and he lived in Italy, and so they burned him at the stake. And you can go to Rome right now, and you can see the plaque where they erected the stake, and they burned him right there. So it was a real thing that to say something out of the box back then was a dangerous prospect. Now, you might think this is a little odd that I'm speaking about hunting for planets around other stars. Isn't this something that the Hubble Space Telescope can do? Why can't we just point the Hubble at a nearby star like Alpha Centauri or Tau Ceti and see the little dot of light that would be reflected off of the planet, making a dot of light next to the star? And the reason that's hard, very simply, is that stars are about 10 billion times brighter than any of the planets that orbit them. And indeed, the distinction, you might wonder, between a planet and a star is that stars generate their own energy by nuclear reactions in their centers, as our sun does by fusion, whereas planets are too cold, not dense enough, and they don't generate nuclear reactions at all. So our Earth doesn't generate any of its own energy. There's a little bit of radioactivity that's cooking away in the interior of the Earth. But by and large, planets are distinguished from stars in that planets don't generate their own energy by nuclear reactions, so they're very faint. The analogy is, here's a lighthouse that is the analog of the star, and there could be a firefly sitting on the structure of this lighthouse, and you'd never see the firefly because it's just too faint relative to the star, the lighthouse itself, lost in the glare. And so it would be with the Hubble Space Telescope. If you pointed at a nearby star, there might be planets orbiting Alpha Centauri, but even the Hubble can't see them because those planets would be 10 billion times fainter in reflected light. And of course, you can calculate that yourself. And one of the things I'll do during my lecture today, I'll sort of divide my lecture up into the astrophysics for 45 minutes, then we'll take a break, and then another 45 minutes if you're still awake by then. One of the things that I'll try to do is give you a sense of the underlying mathematics and physics. I'll try to be gentle about it. And this is very simple geometry. Here's your star. Here's a hypothetical planet. It has, if you sliced it down the equator, it has a cross-sectional area of pi r squared. So its area divided by the area of the entire sphere out to which the light from the star is traveling, that fraction of the star's light that hits this whole sphere that's blocked and reflected by the planet is just this fraction, pi r squared, the area of the planet, divided by 4 pi r squared, the area of this giant sphere, where capital R now is the distance to the planet. You can calculate that fraction for the Earth around the Sun. Its cross-sectional area, the Earth's divided by the 4 pi distance squared from the Sun to the Earth. And you see that the Earth blocks and could presumably reflect about 10 to the minus 10, 1/10 billionth of the light from the star. So there you see it. Our Earth, even if it were a perfect reflector, would only shine at 1/10 billionth the brightness of our sun because the Earth blocks so little of the sun's light that's passing outward. And you can calculate that for any other planet like Jupiter or Venus, and it's about 1/10 billion. So planets are ridiculously faint, and that's why even our best telescopes can't detect those planets. And so we've developed a new technique, and astronomers are using this now all over the world. The idea is that a star orbited by a planet is yanked by that planet gravitationally. Makes sense? A dog can pull on its owner that's more massive, and a planet can yank on its host star with the leash being gravity. And so the two of them orbit a common center of mass, and this is a very powerful technique, of course, because now you can detect the presence and the properties of the planet by watching not the planet, but the star. You just watch the star and see it wobble, yanked gravitationally by the planet, infer the existence of the planet, the orbital period of the planet, and even the mass of the planet, because the more mass of the planet, the stronger it yanks gravitationally on the star. Yeah?
Is it assumed that every planet has gravitational?
Yeah, every planet must exert a gravitational force on other mass in its vicinity. It's one of the physics properties of all mass. They have gravity. Our Earth gravitationally pulls on, let's say, the moon, keeping it in orbit. And the Earth, of course, gravitationally pulls on you. Otherwise, you'd float up above your seat and fly out the room. Yeah.
I don't know how many planets there are around the star.
Yeah, I'll get to that. I'll definitely talk. You're quite right. That's a brilliant point. There could easily be several planets, each of which tugs gravitationally on the star. In that case, the star will do a more complicated whirligig motion, and you'll see some of that. Yeah.
So that would mean that our distance from the sun also undergoes wobble because of the other planets in our solar system.
Yes, our own. You mean the Earth's
Yeah.
distance? Yeah, that's right. We on the Earth, our Earth is being, of course, held to the sun by the gravitational force of the sun, but Jupiter pulls on the Earth as well. The moon also pulls on the Earth, actually. So the Earth is kind of wobbling around a little bit due to the myriad gravitational forces acting on the Earth due to all the other massive objects in the vicinity. Yeah. So this is the basic idea that's been powerful, and I'll introduce you to something I think you actually already know, a quantity momentum that you remember from whatever physics or chemistry class you took a long time ago, or maybe recently. That momentum is the mass times the velocity of an object, and momentum has to be conserved. So this star has a mass and a velocity, mv, and the planet has a mass and a velocity, and those two have to be equal as the planet and star orbit a common center of mass. So you can equate these two, and we'll make use of that momentum conservation in a moment. Now, our sun, of course, wobbles around due to all the 8 major planets and the smaller objects yanking on our poor sun. And you can see where our sun was, our own sun, here in our solar system, where it was in 1960, 65, 70, 1985, 1990, and so on. Here it is, 2025. Our sun does a little dance because the planets are yanking on it. And so in principle, if you lived on another star, like if you lived at Alpha Centauri, you could look at our sun, infer the presence of multiple planets. You see that the motion of our sun is not a perfect circle because it's not just Jupiter that's pulling on our sun, but many, all the planets and the asteroids and comets as well. Here's a little more of the physics of the problem, how we make use of this. Yeah, the star wobbles around a common center of mass with the unseen dark planet. As the star does this, occasionally the star is approaching our telescopes at the Earth, which tends to compress the light waves emitted by the star. Half an orbital period later, the star is moving away from the telescopes here at the Earth, and so the light waves are stretched out. And this is an effect you're all familiar with called the Doppler effect. The Doppler effect simply changes the wavelengths of the light waves when the stars are coming versus when the stars are going. And so we can measure this Doppler effect by looking for the light waves changing their wavelengths as a function of time. Here's a little movie that shows how that works. There's the star. You see it wobbling because of an unseen planet. And when the star is coming at us, the light waves are compressed. When the star goes away, the light waves are stretched out. And our eyes, and indeed spectrometers, can detect this stretching and compressing of the light waves as seen here. The wavelengths and therefore the colors of the spectrum, blue, green, yellow, and red, actually shift from left to right, toward the blue and toward redder colors, and back and forth. So that's the basic idea. You watch for the colors or the wavelengths of light to shift in a periodic way. And you could imagine, again, living on another star and watching the Doppler effect of our sun's light, our own sun here. And you would then, of course, make a graph of the inferred velocity of our sun as measured by this Doppler effect over the course of time. And here again is 1960, 70, all the way up to 2020. And of course, our sun wobbles around by virtue of the planets pulling on it. And so the component of the sun's velocity toward you from far away or away from you is plotted here. And you see the sun has its velocity go up and then down and then up and then down and up and down with a typical speed of about, well, it's only 10 meters per second. I'll get back to that in a moment. But you might ask, what sets this period? Why is there a peak here, then the velocity goes down, then the sun's velocity is high again about 12 years later? Well, that 12-year period is a telltale sign that our sun is orbited by a big, massive bully that takes 12 years yanking the sun as it goes around. And that bully, of course, is Jupiter, the biggest planet, the most massive planet in our solar system. Saturn, the second most massive. The Earth is rather puny, hardly makes much of a difference at all. So you can infer not only that our sun has a planet like Jupiter, but you know what its orbital period is, 12 years. What's a little daunting about this graph is this 10 meters per second. You probably know that Olympic runners run the 100-meter dash in about 10 seconds, 10 meters per second. So our sun and other stars are moving in space in response to their planets by human running speed. That's not very fast on a cosmic distance scale. So we have the challenge to measure the speeds of stars by the Doppler effect at plus or minus sort of human jogging speed to be sure that a star really was seen running. And my team's been working on this for a long time, almost 20 years, trying to make these measurements. There's a team in Switzerland that also has been trying to do this. We do it in Northern California here. This is the Lick Observatory that's about a 45-minute drive from right here at Stanford. You drive east of San Jose, and on top of Mount Hamilton is this telescope. And there's a fantastic spectrometer at the basement of that telescope. And a spectrometer you might not all be familiar with. It's just an optical device that takes the white light from a star and spreads it out into its composite colors, blue, green, yellow, and red, or in other words, wavelengths of light. And here's how it works. The light comes in from the star. It goes through this optics, hits a diffraction grating, prisms that split the light into all of its colors, and then a camera brings the light to a digital detector, like a digital camera at the back. Like that little device right there, has 3 CCDs. It even says so on the side of it. And here we have also, in fact, 3 CCDs that detect the spectrum of colors from the star. And here's what it looks like at the telescope. If you drove 45 minutes from here up to the mountains, you'd see this in the flesh, so to speak. Here's the spectrum from a star, the blue, green, yellow, and red. It's a little complicated, but the basic idea is that these dark spots represent specific colors or wavelengths of light at which the light is absorbed. Indeed, absorbed by the atoms in the atmosphere of the star as the poor photons try to leave the star. So we see, as you can tell, hundreds, even thousands of these dark spectral lines, absorption at specific wavelengths by those atoms. And what happens is when a star happens to have a planet orbiting it, the star has a Doppler effect to its light, and we see a shift like that. We might come back a month later, take another spectrum, go back to the telescope, take another spectrum, we see another shift. That's representative of the kind of Doppler shift we see. And then if we come back yet another month later, we should see this shift reverse, because after all, the planet is orbiting the star, and the star is responding by wobbling around, so we should see the Doppler shift go back in the other direction. And this thing should go back and forth as the planet orbits the star, yanking on the star back and forth. So that's the Doppler effect as we see it at the telescope. I've slightly exaggerated, however, the actual effect. And I have to tell you now that I've kind of lied. And the lie is that here's a CCD with 4,000 pixels that detects all these colors. The actual shift due to a Jupiter-like planet is more like 1/1000th of 1 pixel. So the actual shift is much smaller than I showed you. So we need to analyze this spectrum that you see here with a computer, building a computer model, and actually statistically looking for the Doppler shift. You might say to yourself, how can you measure 1,000th of a pixel? Well, here's how. You actually watch carefully one absorption line, and you magnify it on the computer. And there's the absorption line, spectral line, Doppler shifting back and forth. And you see what happens. As the spectral line Doppler shifts back and forth, the amount of light in the neighboring pixels changes. See, here's a pixel where the amount of light goes up and down, up and down. All these neighboring pixels are pistoning in the amount of light as the months and the years go by, the planet orbiting the star. So we actually can detect sub-pixel, indeed millipixel, Doppler shifts by just simply measuring the amount of light in neighboring pixels. And that's all done digitally, of course, on the computer, so it makes it a lot easier. So that's the story. Now a little history. In 1995, the first planet was discovered around another star by the Swiss team in Geneva. And here are my friends, Michel Mayor and Didier Queloz, who did this work. They worked at an observatory called Haute-Provence. Where's my French major? Haute-Provence in the south of France. Here's the telescope. And they looked at a star called 51 Pegasi, which is now a famous star. And what they saw was that the star did show a periodicity in the Doppler shift, indicating that it had a planet. Well, frankly, I didn't believe it. I was very skeptical when I heard about it. I thought this is a claim that's going to go away. So I went with my collaborators to Lick Observatory. Here it is again. And just so happened that very next week, in 1995, when they announced it, I had 4 consecutive nights scheduled for me on this telescope. So I took 4 consecutive measurements, night after night, of the Doppler shift of 51 Pegasi. And here you see velocity versus time. These are days, so-called Julian days, 1 day, 2 days, 3 days, and 4 days. You see we took a handful of spectra at each one of those 4 days. And sure enough, to my astonishment, the velocities really did vary. And the remarkable thing is that the period of the planet orbiting the star, here of course you're only seeing the star's Doppler shift, that's all we're detecting is the light from the star. The period was only 4.15 days, which is what the Swiss team had said. So we confirmed within a week that there really was a planet that somehow only took a miraculous 4 days to go around its star. Remember, our Earth, of course, takes 365 days to go around the sun. So this is a ridiculously tight orbit that whips around the star, taking only 4 days. It made a really big splash. We continued to take data. Here's velocity versus time for a month. And you can see that the planet is clearly confirmed. Nobody doubted it once they saw the star. Remember, this is the star's velocity wobbling around like this in a totally periodic and frankly almost boring way. I mean, you can predict yourself what the velocity variation will be of this star for billions of years due to this close-in planet that takes 4.2 days to go around it. So this was a pretty big deal. Now, of course, you can do a little bit of science. And here again, I'll inject some of the physics of planetary motion. The orbital period of the planet, 4.2 days, just by seeing how long it takes the star to get jerked around. And then there's something called Kepler's third law, which I'll bet everyone here doesn't know. Isn't that right?
Bet they don't even know the first and second.
They don't even know the first and second law. So I'll start you off on Kepler's third law. Forget those first 2 laws. They're no good. Kepler's third law in its simplest form is a marvel. It says, very simply, that the square of the orbital period of a planet is equal to the cube of the distance of the planet from its star, if you use the right units. So if you're clever and you measure orbital periods of planets in units of years and the distance of the planet from the star in AUs, an astronomical unit is an AU. It's defined to be the distance from the sun to the Earth. Earth-sun distance is 1 AU. And so you can test this equation out on the Earth. The Earth takes 1 year, 1 squared is 1. On the right side, the Earth-sun distance is 1, 1 cubed is 1. Yes, 1 equals 1, that works. And that works for any other period or orbital distance. So that's pretty nice because now we can apply it to 51 Pegasi. 51 Pegasi has a period of 4.2 days. So if you stick in 4.2 days here in units of years, you get that 51 Pegasi, the planet, is only a 20th of an Earth-sun distance, 20 times closer to the star than the Earth is from the sun. Now that gives you another opportunity. Any poor planet that close to its host star is going to be blowtorched by the sheer luminosity of a star. And so you can then use some other equations and estimate how hot that planet would get being blasted by the scorching heat and light from the star. And it turns out the equilibrium temperature of the planet is about 1,500 degrees Celsius. Not surprisingly, close-in planets are very hot, much hotter than the Earth, and so hot, as you can see, that water would boil. So there can't be any liquid water on this planet at all. So to go a little bit farther, now let me bring back momentum, just to give you a taste of some of the astrophysics here. I mentioned before that momentum is conserved, mass times velocity of the stars, mass times velocity of the planet. Can we make use of that? Yes, we can. You can solve algebraically for the mass of the planet. What is the mass of this planet? Well, here it is. The mass of the planet in yellow is, you can solve for it by bringing the velocity of the planet to the other side. Here I've done that. So the momentum of the star divided by the velocity of the planet tells you the mass of the planet. Pretty easy algebra. Now, can we solve for the mass of the planet? Well, you can. The mass of the star 51 Pegasi we know because it's a known star of a known spectral type. We can take its spectrum, and by the way, it turns out to be very much like the sun to a very good approximation. Its mass is similar to the mass of our own sun, which is known. But we know a little more about 51 Pegasi from its spectrum, so we can calibrate it against other stars and learn its mass. So we know the mass of 51 Pegasi to within 5 or 10%. The velocity of the star, which is the second thing in this equation, we just measured by the Doppler effect. So you can go to a telescope yourself, measure the Doppler effect of 51 Pegasi, as we've done here, and that's the velocity of the star. And then the one last thing in this equation, and this is the hardest, is the velocity of the planet. How do you know what the speed of the planet is? Well, you actually do know that. Because remember, the speed of anything going in a circle is just the distance traveled around that circle, 2 pi times the radius of the circle. A, remember, is a 20th of an AU. And it does so in a time, the orbital period, 4.2 days. So circumference divided by the time tells you the speed of the planet. So now you know everything on the right-hand side of this equation. You solve for the mass of the planet, and you actually get, I'll try to go back. What do you get? You get 0.45, well, you can't read this, 0.45 times the mass of Jupiter. Crummy font here. This is, by the way, the original plot I made in 1995, October of 95. So this got old font from 10 years ago when I did this. But you can see 0.45 Jupiter masses it's about half of a Jupiter mass. So you can calculate the mass, the orbital period, the distance of the planet, the temperature of the planet. I just want to remind you that it's sort of amazing. We haven't detected this planet directly, nor any of the others I'm going to show you, but we know a lot about it. Mass, orbit, and orbital period, and the temperature inferred from these Doppler measurements of the star, not even the planet. Okay, now, because Stanford is a high-powered university, or so we're told at Berkeley, I'll give you a quiz. Yeah, bummer. Here's your quiz. This is not easy, by the way. And I'm going to give you a minute or two to think about it. Here is a hypothetical measurement of velocity over the course of time. You're seeing 20 days. And the dots represent the measured velocity of this star that obviously has a planet, making the star wobble around, changing its velocity. And here's the quiz question. I'm literally going to ask for a show of hands, A, B, C, or D. And here's the question. From Doppler measurements, see, this is when the professor gets really nervous because she's wondering whether she'll be able to answer this question. From Doppler measurements, a star exhibits the sine wave variation in velocity. There it is. The orbital plane is oriented edge-on to us, so the planet's going around like this. Here's the star. You're seeing the planet's plane edge-on. Very simple. Pancake edge-on. The orbital plane is edge-on to us at Earth, causing the planet to block the starlight. So every orbital period, the planet happens to cross in front of the star, and then the planet goes on its merry way, and then it blocks the starlight again, and over again, every orbital period. So here's your question. At what point on this velocity plot, A, B, C, or D, will the planet block the starlight? I'll give you give you a full minute to think. This is not so easy. Give you a full minute to think about this, and I'll shut up.
Stanford's honor is resting on this.
All right.
I have a quick question.
Yeah.
Is positive and negative...
Oh, thank you for asking. You're absolutely brilliant in asking that question. You get an A right away. That's critical. Positive velocity in astronomies means the star is moving away from you by convention. I propose that you turn to the person on your left, unless you're at the far end, and turn to the person on your right, and talk about this for 1 minute with the person next to you on your left, or whatever, someone close to you. And I'm going to give you 1 minute. I'm going to shut up. I want you to discuss this and come to a decision. I'll call for a new vote after this.
Right, so it's just stopped in front of you, one light, and it starts to race away. On the other side is C. That's gradually reducing velocity. Wait, D is negative velocity. That means it's moving so the shift from negative to positive, I'm counting to 0. I'm not reading the graph. So right, but then it should be A or C. The moment that it's in front of it or behind it, it's set whatever the word for it is, and that's it stops moving forward away. It's briefly positive, really positive. It has to be A or C. The discrimination is which one's behind the sun, which one's in front. When it's behind the sun, it's about to start coming towards it. Negative velocity. No, but it's got to be A or C. When it's B, it's actually on the side. It's racing on the sides. The sides are when it's moving the fastest. Think of it spinning. Over here is when it's moving. On the front and back is when it stops. If it briefly goes and then goes racing away again. Does that make sense? So it has to be one or the other.
So very few people say they've changed their mind, but maybe they just won't admit it. Let's try it again. How many people want D? A lot of people want D. How many about C? Yeah, some people like C. B? No, D. B is really on the outs. And then nobody wanted B, hardly. And then A? It's almost equal numbers. That's amazing. There's only one answer here, by the way. I mean, the planet goes around the star. There's only one time. Well, here's my way of thinking about it, and you can now critique my explanation for this. Let's start with B, because B, I said the star was moving away from you. So let's imagine the star is here. I'm going to build a model of the system right in front of you. Here's the star. I'll let this hand be the star. And then here's the planet. And so they're going around each other like that. When the star is moving away from you, that must mean the planet is coming toward you. So here's the star going away, the planet coming toward you, and then they're going to go around like this. So I think at this point right here, where the star is going away and the planet's coming, 1/4 of a period later, the planet will be blocking the starlight. Yeah?
How do you know it's a planet? Not a faint line.
That's a really good question. How do you know it's a planet? And the answer is the previous couple of slides, we were able to compute the mass of the unseen planet, which I'll put in quotes for the moment because you'd like to doubt that it's, and that's correct to doubt. So we don't know, ahead of time whether it's a planet, whether it's a star that's dark, whether it's some sort of a toaster that's orbiting the star that is yanking on the star. We don't know. So we compute the mass, and that's all we get. And in the case of 51 Peg, remember it came out a half a Jupiter mass. If it had come out 100 Jupiter masses when we were done with our calculation, we would have all said to ourselves, 100 times the mass of Jupiter, that might be, in fact, a star. So we can tell at least the mass, and then it's a matter of semantics as to what mass threshold you call a star when it's bigger than that, or a planet when it's less than that. And it really is basically taxonomy of semantics at that level. Okay, so now several of you have asked, what about this tilt of the orbital plane? And in fact, we don't know the tilt of the orbital planes. Now, if the orbit were edge-on, then life is happy. That's good. Edge-on orbits are simple. You get the full Doppler effect. But what if the orbital plane is face-on? Then the star and the planet are doing this. You see no approach or recession of the star, and so there's no Doppler effect. And yet there's a planet. So And of course, there are many cases in between where there's some arbitrary tilt or inclination angle. So we don't know. And if you use a little bit of trigonometry from your high school class, you can quickly see that what we measure, unfortunately, is not really the mass of the planet, but the mass times the trigonometric sine of this tilt inclination of the orbital plane. And you can kind of work that out, and you might have guessed that it was a cosine or a sine in the first place. So that's what happens. We don't really know the mass of the planet. We only measure this lower limit to the mass of a planet. So here's what we imagine 51 Pegasi looks like. There's the star, looks like the sun. Here's the planet crossing in front. We've never seen this picture. This is not a Hubble photo. This is an artist's rendering. Lynette Cook is an artist in the Bay Area, and she did her best to listen to the scientists and render the planet in silhouette in front of the host star. And of course, we know a lot about that planet from all the science that you've already seen, the physics of the orbital motion in Kepler's third law, and we know the temperature and so on. So this is kind of the summary. We've learned a lot by just watching the star. But of course, we can go farther. Here's a case of a star that you can see with your naked eye. We watched it from here in Northern California. Star 16 in the constellation Cygnus. By the way, it's up this evening in the northwest. I saw Cygnus last night. Here's its velocity by the Doppler effect over the course of a decade. And you can see that the velocity varied. And there's a clear periodicity of about 2.2 years. You can connect the dots if you want. You can see the amount of wobble is 50 meters a second, 5 times Olympic running speed. And if you indeed build a computer program to simulate this planet orbiting the star, you can connect the measurements, these dots, each with their own error bar, and there's the periodicity shown as the dashed line predicted by the computer. And you can see the computer prediction goes through most of the points. Given their uncertainties, the error bars, that's pretty good. So this is a clear case of a planet taking now 2.2 years to go around the star. That's sort of similar to Mars, that takes about 2 years to go around the sun. You can get the mass of the planet. It's 1.7 Jupiter masses. That's all fine from Newton's laws. The one thing that should be bugging you about this graph is that the velocity of the star slowly increases, and then the star is jerked in a few days to a lower velocity, and then the star takes 2.2 years to change its velocity, and then the star is jerked down to a lower velocity. Why, oh why, is the motion of the star so herky-jerky? And of course, I bet most of you know the answer. The orbit of the planet is not circular, but instead somehow eccentric, elongated, elliptical. And so as the planet goes around the star, it jerks on the star when it's real close right there. And here's the computer simulation showing the jerking, the gravitational pull on the star as the planet crosses close. So that works very well. We can use the computer model to determine the orbit of the planet. It goes around like this. The blue lines show, for comparison, the inner 4 planets of our own solar system for reference. You can see this is a planet whose orbit indeed goes beyond that of Mars. It's elliptical, it's elongated, and that should be a little worrisome. All of the planets in our solar system orbit the sun in nearly circular motion. Why, oh why, did we find a planet in this elongated motion? And I'll get back to that in a moment. It's quite a puzzle, still is, in fact. Here's the artist's rendering. There's 16 Cygni b. Here's the planet. It's 70% bigger than Jupiter, so Lynette Cook rendered it as a big fat Jupiter. And the planet, of course, goes around the star like this. Lynette Cook has put something into the image for which we have no evidence at all, namely a moon, like Jupiter's moon Europa. And of course, when it swings in close to the star, this poor moon would have any water on it, ice even, evaporated. And so the moon would probably lose its water. The prerequisite for life would be hard-pressed to be retained. And so you might ask, could this planet harbor life? And I actually would be a little pessimistic, maybe more than a little, because big Jupiter-sized planets are probably gaseous, like our own Jupiter, composed primarily of hydrogen and helium atoms. And so a big gaseous ball like Jupiter, or Saturn for that matter, hard to imagine even a single-celled organism surviving in the atmosphere. It would sink by gravity into the depths where it's hotter and denser, and the cell would be destroyed. So it's a little hard to imagine life evolving on a planet like this, but not impossible. Some people say to me, wait a minute, maybe a gas giant could evolve life that floats, like fish or birds flying or jellyfish that float. Maybe even this moon could be massive enough to retain its water. So here's an image of a big planet with a moon that's so massive that it retains water molecules in its oceans. And so there's a possibility that life in the universe is more prevalent on moons than on planets. You never know. So that's the story with 16 Cygni. And I'll now touch on this eccentric orbit issue, which is quite wacky. Here's a graph showing all the eccentricities of all the planets we've found as the red dots. Orbital eccentricity is a quantity that goes from 0 to 1, 0 being a circular orbit, 1 being a highly elongated orbit. And you can see that most of the extrasolar planets, or exoplanets as they're often called, have eccentricities that are intermediate. Here's the Earth for comparison, a very low eccentricity, a circular orbit, and yet all of these exoplanets have high eccentricities. So the indication is that other planetary systems typically have their planets in elongated eccentric orbits, not the nice circular orbits that we see in our own solar system. That's a shock. Nobody expected this. We still don't completely understand why this is. The average eccentricity is 0.25, and even the far out Jupiter-like planets, way out more than 1 AU from the host star, even they have large eccentricities. So even the analogs of our own Jupiter are somehow getting these large eccentric orbits. So that's an amazing attribute of other solar systems, and it might bear on habitability, because you could ask yourself, if the Earth were in an elongated orbit, bringing it close to the sun, and then far from the sun, and then close again, could the Earth harbor life? Would the Earth still be habitable if it were heated up by the sun and then frigid cold when it's far, and then heated and then cold, and so on? These planets, I think, would have such temperature swings, making life seriously challenged. Here's a set of data that's quite interesting and bears on a question that was already asked. Here's velocity over the course of time. You're seeing 6 or 7 years. And look at the dots. Yeah, the star wobbles, but there's a short period wobble taking about 2/3 of a year, and then a long period wobble, indicating that there are in fact 2 planets. You can decompose that velocity variation into the 2 underlying wobbles of the star due to each planet. Here's the short period planet, the longer period planet. There are 2 planets. There's no doubt about it. It's like if you close your eyes and your friend plays 2 notes on the piano, you know that there were 2 notes played. If you have perfect pitch, you even know what those notes are. And here we can hear the 2 frequencies of the starlight telling us that there are 2 planets. So there's many planetary systems out there that we've found. By the way, about 31 now we have total, 31 different stars with 2 or more planets that have been discovered by this Doppler method. Here's another one. There's the inner planet, the outer planet. Both planets make a weird pattern. And this is a special case because the inner planet takes 458 days, the outer 918 days. And if you do the math, you see that the ratio is about 2 to 1. So this is a weird case where the outer planet goes around, the inner planet goes around twice for every orbit of the outer planet. So it's called a dynamical resonance. One of my favorite systems is this one. I'll go through it quickly because this is amazing. This is the star in the constellation Cancer, star 55. Here's velocity versus time. Look at this mess of Doppler measurements. You can see faintly a periodicity like so, taking maybe a decade or more. But obviously the velocity is varying due to other planets. And here's how you do this. There's an analysis called Fourier analysis. Probably all of you have heard of Fourier analysis. Some of you may know more about Fourier analysis than I do. But here's an example of how you use it. You take the data, you run a Fourier analysis, and you learn what the embedded periodicities are in your data. These data that I just showed you have a periodicity of, there's the decade, more than a decade, 14 years showing up, and another invisible, previously invisible periodicity taking only 14.6 days. So 14 years, 14.6 days. So there are two planets orbiting the star, one in close taking 2 weeks, and the other taking over a decade. What we do then is really spectacular. You can then build on the computer a model of the star orbited by these two planets and predict the velocity of the star. With that prediction, you can subtract the prediction from the actual observed velocities. What's left over are velocity residuals, as we call them, and then you can take a Fourier analysis of those velocity residuals to look for even more periodicities that you might not have seen in the first pass. And here's what you get. The velocity residuals, after removing the other two planets, shows a third planet hiding in the data. This one takes 44.3 days to go around the star. Now you should play the same game again. Build a model on the computer with 3 planets, subtract the predicted velocities from the observed velocities, take a Fourier power spectrum of those velocity residuals, and here's what you get. A whopping signal at 2.8 days, meaning that's a 4th planet. Play the same game, subtract that one from the data, and you're left with yet a 5th planet. And so this process of building a model on the computer, making a prediction, and then comparing the prediction to the observation itself allows you to check to see, is your model adequate? And if not, what's left over, and what's left over must be yet something else. And so this is a system that actually has 5 planets. We're very excited about it. We only announced it last year. Deborah Fisher on my team was the lead scientist, and she really discovered this thing, going to Lick Observatory every month for about 10 years. Here's what it looks like. Here's 55 Cancri. There's the star. There are 4 inner planets and 1 Jupiter-like outer planet. And for comparison, here's our solar system with the Sun, Mercury, Venus, Earth, habitable zone, Mars, and Jupiter, and then Saturn. So interestingly, the architecture of 55 Cancri is reminiscent of that of our solar system. 4 inner planets, all fairly small, by the way, and then an outer Jupiter. So it really is kind of an interesting case, 55 Cancri, of a system that reminds us a little bit of home. Here's Lynette Cook's rendering of it. There's the star 55 Cancri, the inner planets, the outer planet. Here you see them magnified down below. It's the first and indeed only quintuple planetary system known. Pretty exciting. We're still looking for the 6th planet, by the way. We haven't given up. Here's my favorite system of all time, Upsilon Andromeda. You can see it in the night sky yourself. It's a very bright star. The way you find this star in the night sky here at Stanford, look up, drive to the Andromeda Galaxy, turn left. There's the star right there. You can pick it out against all these other stars. It's the one with the little turquoise arrow there pointing right at it. That helps a lot. And here's the velocity measurements we've made at Lick Observatory. Velocity over a decade. What a mess. Obviously, a Fourier power analysis would be the way to go. I'll do something even easier. Let's zoom in on these little velocities here. Look at how the velocities go up and down. And the period is 4.6 days. You're only seeing 2 months here. So this has an inner 51 peg-like planet. We can, of course, subtract it, look for other planets. You bet they're there. You can see, if you're good, 2 other planets here. There's a 2/3 of a year periodicity, a middle planet, and then an outer planet taking 4 years. So there are 3 planets orbiting this star. We, of course, haven't seen any of them, but here's the civil engineer's sketch. Upsilon Andromeda, the star, the inner planet taking 4.6 days, the middle planet, and then the outer planet. We know their masses, 4 Jupiters, 2 Jupiters, and then it turns out 0.6 Jupiters. By the way, we have no names for any of these planets. You might wonder, has anyone named these planets? Have Did Coca-Cola try to name one of them? Do we have a Planet Pepsi somewhere? None of them has names. So we're still trying to look for a naming scheme. If any of you have a good idea, should we name the planets after, Greek goddesses or something? I don't know. So with this technique, we're beginning to get down to planets that are nearly the mass of the Earth. And with regard to habitability, most of these planets are orbiting so close that they're blowtorched on the hemisphere facing the star, but the hemisphere away from the star is dark and cold. And so there might be a domain in between where the temperature is lukewarm, where the water, if any, would not be boiled away, not be frozen into ice, but might be in liquid water form suitable for biochemistry. Yeah.
How do you we know Mercury is that way, but how do we know other planets are that way?
Yeah, these planets that are close in would have tides raised on them. And so one side of the planet, that hemisphere would be locked to the star and would be continuously blowtorched. And the other side would be continuously dark and cold due to the tidal bulge that gravitationally keeps that hemisphere toward the star, just as our moon, as you all know, keeps one face toward us on the Earth at all times. And then I'll just finish in a few minutes, and then I'll come back and do a closing 30 minutes after we break with this transit method, a totally different method for finding planets. As you can imagine, when a planet crosses in front of a star, it blocks some of the starlight. So if you measure the brightness of a star, even if you can't see the planet, the star dims and then comes back again to full brightness, thereby allowing you to detect the planet and measure the size of the planet. So the planet, when it dims the starlight, the area, the cross-sectional area of the planet, pi r squared, divided by the area of the star, its cross-sectional area, that ratio tells you the radius of the planet. The bigger the planet, the more starlight is blocked. And I think I have a little animation, little animation showing this. Yeah, here we go. There's a planet crossing in front of its star, and you could imagine with a telescope measuring the brightness of a star, watching the star's brightness dim and then brighten up again. And there are astronomers all over the world using their relatively small telescopes, watching stars night after night after night, hoping to catch a star that dims because of a planet. I'll skip over this. This only says that when you make a histogram of the masses of the planets, there are more small planets than big planets. And you might have guessed that. On the beach, there are more grains of sand than there are boulders, and so it is with planets. Here's a little plot showing all those multiple planet systems, the star on the left, multiple planets on the right. We have a lot of multiple planet systems. And then finally, we'll take a break after this. This shows where those crazy eccentric orbits probably come from. Notice the star, there's 3 planets orbiting the star in circular motion. But watch what happens. 2 planets come too close, and they slingshot each other. One of them ejected from the system, leaving 2 survivors. And those survivors have been perturbed, so that now they are in eccentric orbits, having sloughed off a 3rd planet. And maybe that's the way most of these eccentric orbits, these elongated orbits, come from, that early in the history of those planetary systems, there was a close encounter, and that one of the planets was ejected, leaving some survivors. Yeah?
So why do some planets go so fast, like others?
Yeah, that's a good question. The planets in close go fast because they're pulled around by the gravity of the star. So a close-in planet is just being pulled strongly by that star. It goes around very quickly. Mercury in our own solar system takes only 88 days to go around the sun, whereas the Earth takes 365
Is that a
days.
factor?
It's that and the mass of the star. Yeah. The more mass of the star, the faster the planets are whipped around, and the closer the planets are, the more they're whipped around the star. Yeah.
How would a binary star system affect the orbit?
That's a great question. Here's the quick answer. It's a really interesting question. If you have a star and it has planets, but there's another star orbiting that first star, if that second star stays far enough away, and by the way, half of all the stars you see in the night sky are indeed binary stars. So this is not an idle academic question. So if there's a second star, if it's far enough away, the planets survive with no trouble orbiting that first star. But if that second star is too close, it will gravitationally perturb those planets around the first star, and eventually the system will disintegrate. Those inner planets will get flung out, perturbed by that outer star. So for a binary system to have planets, the planets have to be tightly hugging one or the other of the two stars, or the planets have to be orbiting both stars far out. I think we should take a little break, and I'll come back and talk a little about habitability of planets. What do you think?
That sounds remarkably good. Before we do that, if a student or anyone were interested from the public what the current status of the number of extrasolar planets and, you know, all those wonderful histograms,
Yeah.
would we send them to your website? Or just
Yeah, I have a website, exoplanets.org, and there's another European website that I think is exoplanet.eu, and they're both really good websites with lots of
And the
information.
one other thing I wanted to
Oh,
add.
NASA has an even better website that has everything in it.
No. I always tell students to go to your site.
Yeah.
In the past, we've had Greg Laughlin speak in this class, who has done some of these computer models that you can play with online.
Right.
We'll give you that website if you want to play with doing these derivatives and, you know, playing with adding planets and taking them away and so on. It's kind of fun. So we'll give you that website if you want to play with that.
The sort of discovery of planets, the questions of life on those planets, bears on issues that are well outside science, which makes it very exciting. There's a real human element to all of this. Okay, so I thought I would back up for just a minute before I move on to my thoughts on life and intelligent life in the universe, by telling you where all these planets came from. And in fact, where did all the stars that you see in the night sky come from? And the answer actually is still a bit mysterious to astronomers, but we have some basic ideas. When you look up into the Milky Way galaxy within which we live, with its 200 billion stars, there are clouds of gas. And here's a famous one, the Orion Nebula. And within this cloud of gas that's mostly hydrogen and helium, stars are forming by gravity within that gas. The gas gets clumped, the gravitational pull of one atom for another atom, and all the atoms for each other, pull them closer together, forming stars. These stars you see in the Orion Nebula that you can see in a regular telescope are only about 1 million years old. That's a blink of an eye in the 13 billion year old universe that we live in. So in the last million years, these stars have been cooked up, and you can see it again in a telescope. Here's the Orion constellation, the middle star in the sword that's hanging down from Orion's belt. It's that middle star that is, in fact, no star at all. It's this nebula with baby stars being formed in it. And if you look closely with the Hubble Space Telescope at those baby stars, what you see is this. The baby stars are seen in front of the nebulosity in the background, but in silhouette are these dark smudges around each star. The dark smudges are due to gas and, in fact, dust orbiting the young star like placental material out of which the star formed but left behind. And so the dark smudges show you what is called a protoplanetary disk of gas and dust, a flattened distribution of gook out of which the star formed, and now planets are forming in that material. And I think I have an artist's rendering of one of these. Oh, there's many measurements that have been made of these disks. Here's the artist's rendering. As we think from all the measurements in the infrared and the radio waves that come, here's the young star, there's the nebulosity in the background, and then there's this disk of gas and dust orbiting the star within which planets are congealing, literally condensing out of the cold dust and gas that's orbiting out there. The dust particles collide and form bigger dust bunnies, like the objects that are behind your bed that you don't want to admit to. And those dust bunnies then collide and form ever bigger blobs of material. And so that's the way planets form. Here's another artist's rendering, the young star, the nebulosity of the Orion Nebula or whatever in the background. Here's the disk of gas and dust and a young planet forming out of that gas and dust. Here's yet another artist's rendering of the young star, gas and dust. You see the ices come together quickly. When two snowballs hit, they smush, they compress, they dissipate their energy, and they stick together to make an even bigger snowball. And so you get these comet-like snowy, icy objects that then collide with each other and make ever bigger objects, eventually getting to be the size of planets. And that's how we're pretty sure planets form. There are many other stars that have these disks around them. Some of them look kind of weird like that. And we think that what happens is that the planets, when they form, collide with other planets. Here you see a small planet hitting a bigger planet. They melt, stick, and now are an ever bigger planet than they were before. And that's the way the Earth formed and other planets formed out of collisions among previously formed planets. And so the movie is something like this. You start off with lots of little rocks and pebbles, and they collide with each other. They grow ever bigger into Mars-sized planets, as you see here. And then eventually those Mars-sized planets even collide and make Earths. And you can see evidence of this era of collisions even today, 4.5 billion years after the Sun and our planets formed. The impact craters on the Moon serve as dramatic, violent testimony of the impacts, the collisions that the Moon suffered, and certainly the Earth did too, as giant comets and asteroids slammed into the Moon, slammed into the Earth violently, but made the Moon and the Earth as big as they are today. Yeah.
When does that stop happening? Like then technically would our Earth still be?
Yeah, that's a great question. And the quick answer is that when the astronauts went to the Moon, they took back rocks from these craters, and they can be age-dated by radioactivity of the rocks, radioactive decay of certain elements. And so we know the ages when these craters happened. And it turns out the first 100 million years out of 4.5 billion years when the Sun first formed, the first 100 million years, there were lots of heavy impacts. This so-called heavy bombardment period is what it's called, when there were still lots of, let's call them the debris, asteroids and comets, slamming into the Earth, slamming into Jupiter, building those planets up to the size that they are today. And of course they still happen. Lest you breathe easy, you know that 60 some odd million years ago, a giant comet or asteroid hit the Earth and splashed up so much debris 60 million years ago that the Earth was covered and killed the dinosaurs. So it was a giant impact, a mere, I say, 60 million years ago, because of course it could happen today. And so I recommend all of you sell your stocks immediately because the New York Stock Exchange will certainly suffer when we have a big impact on the Earth.
Mercifully.
Yeah, mercifully maybe, right? Put us to merciful death. So here's another nice picture of what the Earth looked like early on. The Earth had water delivered to it by comets and hydrated asteroids, made the oceans. I can tell you a lot more about this, and I will do so in a few minutes. And so the Earth built up its current size and chemical composition by the incoming asteroids and comets that brought the atoms and molecules with them. Now, what I'd like to spend the rest of the talk on today is looking for habitable planets, truly Earth-like, lukewarm planets that might be suitable for life. And we're looking for these beasts. I'll tell you, you may already know this, but I'll just remind you that we think biology as we know it requires liquid water. That may not be true, but it's our best guess. Anywhere on Earth where there's liquid water, there's at least microbial life. And so, and you're going to hear a lot about that for the rest of the quarter, I promise. So here's an example of this, the star, planets orbiting that star, and there's a zone that's not too close where it would be hot, not too far where it would be cold, but a zone where the temperature, as Goldilocks said, was just right for water to be in liquid form. And of course, that temperature has to be between 0 and 100 Celsius in order for the water to be liquid. And here's another depiction of the habitable zone around any star. There's the star. Planets too close are going to be too hot. Planets too far, the water will be frigid, cold, and frozen into ice. That doesn't seem suitable, or at least amenable to biochemical reactions. But then where in this zone in between, the water's liquid, serving as the solvent for biochemical reactions that we think are critical to make an RNA world and then eventually a DNA world. So that's the notion. Habitable planets are rocky with lakes and oceans with the water liquid. Now, we're going to look for these Earths, and I want to tell you a little about the future, and then I'll tell you a little about life on these planets. The future is extremely exciting. I can't even begin to tell you. I'm jumping out of my socks with excitement about this mission that NASA has designed, built, and it's on its way to Florida for launch in 2 months, literally during the quarter. It's called Kepler, and it's merely a spaceborne telescope that will be launched into space, trailing behind the Earth, monitoring the constellation Cygnus, looking at 100,000 stars for any of them that dims as an Earth-like planet crosses in front of those stars. So this Kepler mission will be looking for exactly this scenario that we've already talked about. Launch, literally designed and built here at NASA Ames, just a few miles down Highway 101. And so it's very exciting that Kepler is about to be launched. Here's a movie showing you what Kepler will do if we're lucky. This is what the telescope looks like. It's only a 1 meter diameter mirror. So it's actually a medium-sized telescope. But in space, it's particularly powerful. And so we'll aim it at the Cygnus constellation where there are hundreds of thousands of stars and hope to monitor the brightnesses. Literally, within the next couple of years, we will get results back from Kepler with the hope of detecting the first Earth-like planets ever discovered. So far, we've found none because they're just so little. They make such a little difference. And here's our galaxy, Milky Way galaxy, the Earth, and here's the Cygnus area that we're going to be hunting in, Earth hunting in. In fact, you can look up into the night sky tonight. Cygnus is here again in the northwest, and here's the field of view of the Kepler telescope. So it's pretty exciting, not just within our lifetimes, but within the next couple of years, we hope to find other Earths. So other Earths are probably out there, and the only question that's left is how many of them are habitable? How would we know when a planet is habitable? What are the conditions that render a planet habitable? What kind of an environment does an Earth have to have? And actually, your professor knows way more about this than I do, so I'm going to just advertise what I presume are at least 1 or 2 talks you're going to give.
Oh, many.
You'll be bored by the time you're done hearing all of her lectures. But here's what
After one.
here's an ad for the lectures that she's going to give that actually for which she's the world's expert, and that is studying habitability by ironically going to one of the least hospitable places on Earth, namely Yellowstone. Right now, there's 5 feet of snow everywhere in Yellowstone, and yet the geysers are spewing out boiling water. What a contrast in temperatures. And, as she will describe to you, the water in many locations is heavily acidic. You can go to the hot springs of Yellowstone and ask yourself, in this place under 5 feet of snow, where the water is boiling and the water is acidic, is there any chance for life? And the answer is, it turns out dramatically, yes, there is not only a chance for life, but life thrives here. This is my favorite place anyway, Grand Prismatic, but I'm just an amateur. Here's another hot spring where you see different colors, and as your professor will describe to you, the different colors represent different bacteria and the pigments of them that can be studied for their habitability and the way they've adapted to this acidic environment. Being an amateur, I brought pH paper to check on the experts, and sure enough, the pH was 2. If you remember your high school chemistry class, pH of 2 is very acidic, and yet there's these beautiful filamentous bacteria thriving in nearly boiling acidic water. here's my second favorite place, churning cauldron, where you can see the water literally boiling. You can toss in pH paper if you dare to do so and verify that, yes, the pH is in fact 2. Here's the clip that I attached it to because I was scared to death. The black clip is no longer black. And then, as if to laugh in my astronomer face, the algae was drawn up on the string that I had thrown into churning cauldron, proving without even a microscope that there are life forms that are partying there in the boiling acidic water. And so you'll learn a lot more about this later in the semester. For me as an astronomer, the message is dramatic. What these little microbes have taught me, and I don't know anything about biology, is that critters can tolerate extraordinary extremes of temperature. They don't care whether the water is acidic or alkaline. They don't need sunlight or specific food sources. They thrive anyway. And so I think the best conclusion that even a school child could draw from this is that where you have liquid water, pretty much no matter the chemistry there, there's a chance, at least, for primitive microbial life. And that tells us that the Earth's out there, that surely are out there, that are hotter than our own Earth, colder than our own Earth, nonetheless probably have the right conditions for life. We have all the ingredients for life on other planets, the Petri dish itself. We certainly have the carbon-based molecules. Clearly there's water elsewhere in the universe. It's one of the most popular molecules. Some of it will be lukewarm into liquid. And the energy is there in the form of solar or stellar energy, tides, geothermal, and so on. So I think if you ask molecular biologists, is there life in the universe? Is there any real chance for life in the universe? They will almost be unanimous in saying yes, at least microbial, simple life. Maybe it's based on RNA, DNA, or some other replicating molecule that we haven't discovered yet, but certainly some kind of life seems to have a good chance. And so I'll just finish with a handful of slides that are designed to be provocative. Later in this quarter, you're going to have a famous astronomer come and give you a talk named Frank Drake. And Frank Drake is one of my best friends, one of my best colleagues, and he's going to tell you how they're searching for intelligent life in the universe and how, if we look long enough and hard enough, we will eventually find intelligent life. I'm going to try to rebut that argument before he has a chance so that you can then rebut him when he comes here, but just don't tell him that I told you so. Here's the rebuttal to Frank, and I'm of course kidding because we're all friendly scientists trying to just get the answer, which we don't know. Here's the way you can look at intelligent life in the universe. I'll give you my view of it. There are many, many planetary systems in the Milky Way galaxy, billions of them, many of them older than the Earth, and so you can ask, what fraction of those planetary systems have intelligent life? Well, nobody knows the answer. Nobody knows what fraction of planetary systems might spawn primitive life and then have it evolve by Darwinian evolution into intelligence. The most pessimistic answer that Frank Drake gives, and others, is 1 in a million. Maybe intelligent life is a 1 in a million throw of the dice. You start with an Earth-like planet, and only 1 in a million times do the reptiles and the birds evolve into intelligence. If you buy into that, multiply 1 in a million by billions of planetary systems, you end up with thousands of advanced civilizations, and I do mean advanced. Some of them have been around for millions of years past us. So like Gene Roddenberry in Star Wars told us, there must be so many advanced galactic clubs out there that they need stoplights to avoid running into each other. But if that's true, and that's the message we all got as children reading science fiction, if it's true, where are they? Why is it, you might ask yourself, that when you look at the moon, there are no alien spacecraft that landed there and checked it out? There are no obelisks like in 2001. There's no crash debris or telescopes left by an advanced civilization over the millions and indeed billions of years. Are there footsteps on the moon? Actually, yes, there are footsteps on the moon. They're ours. And there aren't any other species that ever walked on the moon as far as we can tell, despite very little erosion. Mars, same thing. Very little evidence of any sort of life ever having been there. not just microbial, but no evidence of advanced civilizations having come there. So it's rather interesting. The Earth, a beautiful Shangri-La, tropical rainforests. We have beachfront property available to the aliens to come and set up their alien hotels and alien golf courses. And they could, of course, have come here over millions or billions of years, set up shop here on the Earth. They didn't do so. Where are the advanced civilizations that are filling our Milky Way galaxy? Moreover, hundreds of professional telescopes watch the night sky. We've never seen a clear picture of a UFO. The night sky doesn't have robotic spacecraft. We don't see gamma rays from them and so on. And the SETI search, which you'll hear about this quarter, the search for extraterrestrial intelligence, has failed to find any radio transmissions, television transmissions from advanced species. So the question really does arise, where are the advanced civilizations if they're really out there? Did we make a mistake in concluding, as we have done in our science fiction novels and movies, did we overestimate the chances of intelligent life in our galaxy? They should have somehow crawled here one way or the other. And there are, in fact, some reasons that I'll just close with today that maybe intelligent life is a longer shot, a more ridiculous throw of the dice than we had thought. For one thing, yes, water was acquired by the Earth by comets and asteroids that slammed into the Earth. But the Earth has only 0.03% water. What if the Earth had twice as much water, 0.06%? Well, then the Earth would be a water world. Covered by water, there'd be no continents. And without continents, I don't see how we could build electronics or spacecraft or violins or any of the things that make our culture or our science. So if the Earth were a water world, intelligent life, let me be more specific, technological life would be hard-pressed to develop. Smart marine mammals, yes. Smart electronics engineers, it would be hard unless we have some continents as well as some water. You also don't want the Earth to be a desert, like Mars and Venus being devoid of water. So the exact amount of water on the Earth is interesting. What about Darwinian evolution? Does it always lead to brainy folks like us? Does Darwinian evolution lead inexorably to a pinnacle of the Darwinian evolutionary tree, us human beings, Homo sapiens? Well, the dinosaurs give you an experiment. For 100 million years, the reptiles loomed over the Earth, the food chain, and during that time, the fossil record shows no evidence of chessboards, no violins, no rocket ships, no pianos. The dinosaurs never evolved, as far as we can tell, tools that characterize a truly technological civilization. So for 100 million years, Darwinian evolution failed to favor big-brained species. Maybe that means that we humans are a bit of a quirk, a twig on the evolutionary tree, not the pinnacle of that tree. By the way, of course, you can ask your pet cat whether it's getting any smarter with time, and you'll see that they aren't. Flies don't know algebra, even after hundreds of millions of years of evolution. Cats don't play Chopin. And so again, these species that we live with all the time have had hundreds of millions of years to get smarter, and they aren't. Even we humans, you might argue, are not getting a whole lot smarter. Maybe we're even moving in the other direction. Another problem, which I won't go into, is simply the travel time among the stars. Maybe Einstein was right, and that it just takes a lot of energy and time to travel from one star to the next. A light year is a long distance, 6 trillion miles, and the nearest stars are several light years away. Maybe it's just too hard to travel like the Star Trek Voyagers did. And I won't go through the numbers, but you can work out the numbers at the speed of light, how long it takes to go from here to Alpha Centauri at a reasonable speed. And it's a long, long time, hundreds of thousands of years. And then finally, I'll raise one last issue. Maybe intelligent life in the galaxy is rare because those intelligent species develop technology which renders them vulnerable to their own technology. Indeed, maybe they destroy each other after a few thousands or millions of years. And you can easily show that an advanced civilization better last long enough for the next advanced civilization to come along. And then it has to last long enough for the next advanced civilization to spring up, evolve, and come along. And that means, if you work it out, that we humans better last for tens of thousands of years to have a good chance living long enough as a species for the next advanced civilization to spring up and for us to be able to communicate with them. So maybe advanced technological life is more like a Christmas tree where the light flickers on and then flickers off, and then another light flickers on, flickers off, and the challenge of surviving as an advanced species is simply too great. And you can even ask yourself, how secure are we humans? Are we immune to our own self-destruction? And so there are a number of reasons why advanced life might be rare. And here's just a summary of what I've just said. And I'll just finish by saying I think the most exciting science going on these days is still SETI, the search for advanced extraterrestrial intelligence. A lot of it's happening here in the Bay Area at the SETI Institute here on the peninsula. And so we can all hope that in the next decade or so, maybe we'll get the first signals of a rerun of, from Alpha Centauri, of their version of Gilligan's Island or something, and that would prove to us that there's no intelligent life on Alpha Centauri for sure. So we're building radio telescopes. The SETI Institute and other institutions like Berkeley are contributing to the detection of advanced life. And so I'll just finish by saying I think you're all lucky. We are going to find Earths in the next few years, if we're at all lucky, by the Kepler mission. And then that will lead to the next question. How common is primitive life in the universe? And how common is intelligent technological life? And of course, at this stage, we really don't know the answer to these final two questions. So I'll stop there.